Assalamualaikum students. Students, in today's class, we are going to discuss intermolecular forces, right? Now, what are intermolecular forces? Intermolecular forces. Look, the forces of attraction between the forces of attraction between molecules. Inter mean between molecules. Like one molecule attract another molecule. The forces of attraction between molecules. These intermolecular forces, they are of two types major. What are the two types? Let me write it again, wait a minute. They are of two types. Hydrogen bond and van der Waals. Hydrogen bonds and van der Waals forces. Van der Waals forces. Van der Waals again are of two types. PD-PD interaction, permanent dipole and permanent dipole interaction. You can directly say interactions between permanent dipoles. Just interactions. And what is the other one? The London forces. The London forces, or IDID or TDID. This I'm going to explain. Now, listen. In which molecules there are hydrogen bonds? Hydrogen bonds are present between polar molecules that have OH, NH, and HF. You know why? Because the electronegativity difference are large and their dipoles are very large. So these intermolecular forces are stronger than these two. And the only reason that these are stronger, the electronegativity difference is more, their dipoles are strong, and they result in stronger intermolecular forces. Now, hydrogen bonds are present between polar molecules that have OH and NH and HF, and permanent dipoles are present between polar molecules that don't have OH, NH, and HF. Like polar with OH, NH, hydrogen bond, polar without OH, NH, permanent dipoles, PD-PD interaction. And ID-ID are present in all simple molecules. Now coming to first another way. We have two types of molecules. Look, we have two types of molecule. Polar molecule and non-polar, no permanent dipoles. Polar again of two types with OH, NH, and HF. Without OH, NH, and HF. Now, listen. The one which are polar with OH, NH, they have hydrogen bond between molecules, they have permanent dipole interactions, and ID present everywhere. So, one thing, in non-polar, there is no other force, only ID between the molecules. Now, the first thing, what is hydrogen bond? I'm starting with this hydrogen bond and then I will go this way, right, to explain. What is hydrogen bond? You know, hydrogen bond. Hydrogen bond, if I show you the notes that you will find on my website, these are the notes which are, I think, describing everything almost. See what I've written? I'm just taking this part, not too much. The rest I'm going to explain over there. Hydrogen bond. Hmm? So, what is hydrogen bond? Listen. The attractive forces between partially positive hydrogen atom that is covalently bonded to FON and the lone pair of electron of the FON of another molecule. What is the meaning of this? Think. Look. Look. The attractive forces between partially positive hydrogen atom that is covalently bonded to F, O, or N in one molecule. Attractive forces between partially positive hydrogen atom that is covalently bonded to FON in one molecule and lone pair of FON of the other molecule. This is partially negative, this is partially positive. You know, actually, this is highly electronegative atom. It attracts the electron pair. When it attracts the electron, this is like very electron deficient region. Look, this is a very electronegative atom, these three. One of them would be there in the molecule. They attract the electron from the hydrogen. As a result, the dipoles are very large because the electronegativity difference is very large. When the electronegativity difference is large, the dipoles are large, the intensity of the positive charge is very high. It will attract the electron of another FON very strongly. Look, what I've written here. Fluorine is very electronegative, attract electrons from the shared pair. The dipoles are very large. This hydrogen feel very deficient of electron, so the dipoles are large. It attract strongly the electron pair of the F. This is called hydrogen bonding. The attractive forces between partially positive hydrogen atom of one molecule that is covalently bonded to FON and the lone pair, the forces between the H and the lone pair of FON of the other molecule. Now, if you see, After this description, you are at certain conclusion that if it is the case, if it is this way, the hydrogen would be definitely get sandwiched between FONs. For example, I have a molecule, ammonia. This is ammonia. Is the ammonia contain NH? Yes. There is another ammonia. The hydrogen of this bonded to nitrogen. The nitrogen is very electronegative, attract electron very strongly. The dipoles are very large. Will this hydrogen attract the lone pair of the nitrogen? Yes, of course. This hydrogen bonding. But how you're supposed to write, to draw the hydrogen bonding? This way. Look, this is NH3. This is partially positive, partially negative, attracting what? Lone pair of the nitrogen of the other molecule. Partially negative. This is hydrogen bond, right? It is most of the time for 3 marks. You know, how is the distribution of the marks? The lone pair 1 marks, the negative, positive, negative another mark, and this dotted line another mark. Now, if I ask you that is there hydrogen bond between ammonia and water? Ammonia and water? Yes, of course. How? This also contain NH, OH, and they can do hydrogen bonding. And now, what will happen? This is partially positive, partially negative. The H will attract the lone pair of this. And there is another possibility. This is partially negative, partially positive. It can attract the lone pair of the nitrogen. You can draw it in both way. Both are 100% correct and both are possible in the same mixture, right? So, if this is ammonia, the hydrogen will attract the lone pair of the oxygen, yes. Or, first let me put the charges negative, positive, and negative. Perfect. This is hydrogen bond. Now, if the hydrogen of the ammonia attract the lone pair, another possibility, the hydrogen of the water attract the lone pair. Yes. Suppose this is water attracting lone pair of ammonia. Of course, this is partially negative, positive, and partially negative. This is hydrogen bond. Now, one thing is the hydrogen getting sandwiched between nitrogen and oxygen? Yes. Is the hydrogen getting sandwiched between oxygen and nitrogen? So, what I told you? That when there is hydrogen bonding, the hydrogen will sandwich between FONs. Right? Next, listen. If this is HCl, oh, okay, let me explain with HF. This is HF, right? There's large electronegativity difference between H and F, large electronegativity difference. The F attract the electron. The hydrogen is very deficient. It attract the electron of the F, of course, very strongly. The dipoles, it's called hydrogen bonding. Now, if this is HCl, this is what? HCl. Is the electronegativity difference between H and Cl is large? No, not that much. So, it is also having positive negative. It is also having positive negative. But you know, electronegativity difference is not very large. Not very large. So the dipoles are not that much strong. are not that much large. So there are permanent dipoles. It's a permanent dipole. It's a permanent dipole. A permanent dipole. A permanent. Will they attract? Yes. So this is called PD-PD interaction. A permanent dipole attracting the permanent dipoles. So if you see there is strong similarity between hydrogen bond and PD-PD. But what is the major difference? The electronegativity differences are large, their dipoles are large, therefore the hydrogen bonds are stronger than the PD-PD. So, if there is, suppose H2O, partially negative, partially positive, its lone pair is attracted by what? This partially positive and negative. This is hydrogen bond. Because hydrogen bond is present between all the molecule where there is OH and H and HF. And what is the other thing that will clear cut indicate there is hydrogen bond? The hydrogen gets sandwiched between what? FONs. It's getting sandwiched. Now, suppose there is this H2S. There's this what? H2S. This is partially negative, partially positive. Now, what you will call this? Is this hydrogen bond? No, it's what? PD-PD interaction, right? It's not hydrogen bond. So, in hydrogen bonds, what I told you, that the hydrogen that is partially positive covalently bonded to FON, attracting the lone pair of FON. And second, the hydrogen gets sandwiched between FONs. If the hydrogen is not between FONs, you will not call this hydrogen bond. You will call it what? PD-PD interaction. So we discussed the PD-PD. It's like there is no more information. Like it's exactly this thing. This is your course. Like the partial positive atom of one molecule attracting the partial negative of the other. Now, the hydrogen bond in water are strong, or the hydrogen bond in HF are strong. How you will compare the hydrogen bond of one molecule with the hydrogen bond of another molecule? What are the criteria? You know what you're supposed to do? Hydrogen bond depends on what? Hydrogen bond depends on number one, electronegativity difference. If more, the dipoles are large. The dipoles are large. Like hydrogen bond depends on the electronegativity difference. Even if I have to compare HF with H2O, if the electronegativity difference is large, if the electronegativity difference is small, definitely the attraction of the HF would be stronger than the attraction of the HO in water. Now, the next difference, I'm going to make it more clear. Give me a little bit of time. Listen. The other difference, like one is electronegativity difference. You know, what is the next difference? The next difference is average number of hydrogen bonds per molecule and maximum number of hydrogen bond per molecule. A very important point. Listen, listen. For example, I have water. I have ammonia. Now, one difference. Across a period, hmm? Across a period. This is lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine. This is period two. Across a period, electronegativity increase. So which one is more electronegative? Oxygen. So if the oxygen electronegativity is more and its electronegativity is small, so the difference of the electronegativity difference of HO is more, its dipoles are what? Large. The dipoles are large. The dipoles are small. One big difference. Second, how to count the maximum and the average. You know what you're supposed to do? You have to, if I copy it from the notes, listen, how to find, look, comparison between molecules that contain hydrogen bond, more electronegativity difference, larger dipoles, and more is the average number of hydrogen bond per molecule. But how to find maximum and the average number of hydrogen bonds? Listen, how to find the maximum number of hydrogen bonds and average? First, sum of lone pair of the electron of FON and the number of hydrogen atoms bonded to FON in a molecule is the total number of hydrogen bond per molecule. What is the meaning of this? Look, the sum of the lone pair of the electron of the F and the number of hydrogen atoms bonded to FON. This is a molecule. You can see this is a molecule. What is the number of lone pair? 1. What is the number of hydrogen? 3. Look, it has one lone pair. It has 3 hydrogen. And the sum is how much? 1 plus 3 is what? 4. So what is the total number of hydrogen bonds per molecule? 4. It can make 4 hydrogen bond at max. It can do how much? 1, 2, 3, 4. But listen, what is the average number of hydrogen bond? For average, look, among lone pair and hydrogen, you have to check that which one is less, smaller. So which one is smaller? 1. Look, you have to count all the hydrogens and the lone pairs bonded to FON, right? To find the maximum and the average, your first thing is count the hydrogens and the lone pair bonded to FON. Now, the total number is the maximum number of hydrogen. But among the total, if the lone pair are the smaller, then it is the average. But if the hydrogen are smaller, then they are the average. So what I've written, one pair are less, then one lone pair is less than 3 hydrogen. Therefore, 1 hydrogen per molecule on the average. Right? Look, I'm going to explain this to you. Come, taking another example. See? For example, you have HF. Count all the lone pairs and the hydrogen bonded to FON, whatever is your molecule. So there are 3 lone pairs and there is 1 hydrogen. So what is the sum? 3 plus 1, 4 hydrogen bonds per molecule is what? Maximum. This is what? Maximum. Right? Now, among these lone pair and the hydrogen, which one is smaller? The hydrogen is smaller. So, 1 hydrogen bond per molecule. Average. Average. Now another example. Suppose this is H2O. This is what? H2O. How much are lone pair? Two are lone pairs and two are hydrogen. So four maximum. Four is what? Four hydrogen bond per molecule is maximum. And two and two are equal. So what we can say? Two hydrogen bonds per molecule is average. It's what? Average. Now, another example. Another example. For example, this is methanol. So you're supposed to count what? The hydrogen and lone pair bonded to, yeah, with FON. So you are supposed to count the one which are with O, not with the carbon. So there are how much? There are two lone pair and there is one hydrogen. Two lone pair and one hydrogen. So total maximum three hydrogen bond per molecule, but average one hydrogen bond per molecule in methanol. Clear? Coming to PD-PD interaction. I hope you understand that in any molecule, if there is hydrogen bonding, like for example, okay, before proceeding toward PD-PD, last comparison, like suppose if I compare water with ammonia. So what are my two comparison? Look, what are my two comparison? The electronegativity difference is more. The electronegativity difference is less between N and H, between O and H. So the dipoles are what? Large. 1 point. Second, two hydrogen bonds per molecule. Average. One hydrogen bond per molecule. Average. Why? Because there is one lone pair, three hydrogen. So which one is small? Lone pair is small. There are two lone and two hydrogen. So on the average, two. Look, suppose I have 10 HF or 5 HF. For instance, 5. It's like this. It has a large number of lone pairs. But hydrogens are very small. There are three hydrogens. Sorry, one hydrogen and three lone pairs. Now, another hydrogen. There are 5. For example, look, there are too many lone pairs, but only one hydrogen available. If there is only one hydrogen available, so they can maximum do how much hydrogen bonds? Definitely one. So if there are 5 hydrogens, sorry, 5 HF. So 1, 2, 3, 4, and even I can go for this. How can I make it 5? Yeah, I can connect this to this. Look, so 1, 2, 3, 4, 5. In HF, there are many lone pair, but hydrogens will be less. Therefore, the average number of the hydrogen bond depend on the one which is lesser. right? So the lesser is the hydrogen is the result. Even if there are many lone pair, there is no hydrogen to bond with these lone pairs. As the result, they are not making hydrogen bond. So it depends on the lesser one. Now in ammonia, even the hydrogen are more, but since the lone pairs are less, so the hydrogen will not be doing hydrogen bonds because the lone pairs are less. So you have to count the lone pairs, you have to count the hydrogen, and the one that is lesser will decide the average number of hydrogen bonds per molecule. And once you are discussing PD-PD interaction, you know what is PD-PD? Huh? The permanent dipole of one molecule attracting the permanent dipole of another molecule. This is PD-PD interaction. This is called what? PD-PD interaction. Now, if there is suppose H2S, this is what H2S, negative, positive. This is not hydrogen bond. Hydrogen bond is only possible in the molecule that contain what? OH and H and HF. So they're not with OH and NH. They are polar. They are polar. Agree. So there are permanent dipoles. There are permanent dipoles. They are attracting. Now, what is the difference between this molecule and this molecule? The electronegativity difference. The one in which the electronegativity difference would be large. The dipoles are large. The PD-PD would be strong. Like I know that in HCl, the electronegativity difference is more. As a result, the PD-PD of this would be stronger than the PD-PD of this. Right? Now the next thing is what? ID, London forces. What? London forces. The scientist was London Fritz, right? Therefore, they're called London forces. They're called IDID. They're called TDID. What is this ID and TD? The I stand for instantaneous or induced, and T stand for what? Temporary. And D stand for what? Dipoles. Huh? So these are the intermolecular forces between permanent dipoles. No, between temporary dipoles. When one temporary dipole attracts another temporary dipoles. What are temporary dipoles? The temporary dipoles are formed when electron cloud get asymmetrical at any instant. At any instant. The temporary dipoles are formed when electron cloud get asymmetrical at any instant. Like for example, this is a molecule. Huh? These are electrons, they are symmetrically distributed. And they're not fixed, they're revolving. There is possibility that at any instant the electrons are at one side. So these are temporary, they're repelling. So these are temporary dipoles. Don't you think that they will induce in the closer molecule, in the nearby molecule? They will induce. Its electrons are repelled, they move to the other side. So this also become temporary, negative and positive. And these temporary dipoles attracting each other is called what? TDID or TDTD interaction. And these temporary dipole, these interaction, they depends on what? It depends on electron. More electron Stronger are temporary dipoles because they are easily formed. More electron, more easy is the distortion of the electron. Like if there are more electrons, they can become asymmetrical easily. The dipoles are formed very easily. Therefore, they are stronger. Right? For example, we have some, like we have done even in O levels. Like in O levels, when you study, this is fluorine, this is chlorine, this is bromine, this is iodine, this is gas at room temperature, gas, this is a liquid. Why? What is the reason? Now tell me. Is the fluorine or chlorine, is there any electronegativity difference? No. Do they have permanent dipoles? No. They have what? Temporary dipoles. They have temporary dipoles. They have temporary dipoles. Now, why they are becoming from gas to liquid to solid, like why they are changing this way? This shows that their temporary dipoles are getting stronger. Huh? The electrons are more, the temporary dipoles are getting stronger. Therefore, they are changing from gas to liquid to solid. And exactly the situation with this. This is P4. This is S8, chlorine argon. Look, these are period 3 elements. Now, is there any difference between 8 sulfur? They're all same. If they're all same, is there any permanent dipoles? No. Any permanent dipoles? No. Permanent dipoles? No. They don't have permanent dipoles. Don't have permanent dipoles. So they have what? Temporary dipoles. Their temporary dipoles depends on what? Electrons. More electron. Stronger temporary dipoles. Now, electrons of which element are more? Definitely sulfur, because there are 8 into 16 electron, 2 into 17 electron, and this is what? 18 electron. This is 4 into 15. So which one have more electron? S8, then what? P4, then what? Cl2, and then what? Argon. If electrons are more, the temporary dipoles are stronger. Therefore, the melting point of S8 is more than P4, which is more than Cl2. Right? Now, another situation. If electrons are same, when is this possible? Inorganic, when you will be studying isomers specially, right? Like the Cambridge target the isomers for that point. When you have isomers, like you have C4H8, huh? You have C4H10, taking the example of this. If you have butane, this is straight chain, and you have methyl propane. Methyl propane. If they are straight chain, the surface area of contact is more. Huh? Surface area is more. The ID or TDID are what? Strong. But if you have this branch molecule, look, the branch has less surface area of contact. So the ID are weak. So if I show you the notes, come to this. Look, first I started with what? With the hydrogen bond, right? The hydrogen bond are in the molecule that contain HF, OH, and NH, right? This is fully explained. You can see this. And comparison of the hydrogen bond is done on the basis of electronegativity difference and average number of the hydrogen bond, and how to find the maximum and the average. This is described completely. Now, the other thing is what? The PDPD interaction. The PDPD is given here. I think it's there. Wait a minute. It described here. Look, that when the electronegativity difference is not very large, then we say that it is what? PDPD interaction. And PDPD interaction depends on electronegativity difference, larger dipole, stronger PDPD. That's it. And IDID depends on what? Come. IDID depends on what? Number of electrons. More electrons, stronger IDID. More electron, then next, and the IDID is getting weaker. And at the end, if I compare all these hydrogen bond, PDPD, and IDID, the strongest one are what? Hydrogen bond. The hydrogen bond depends on electronegativity and average number of hydrogen bond. The PDPD only depends on electronegativity difference. The IDID depends on electron, but if electrons are same, then here I have mentioned that there are two possibilities. Maybe the molecules have same number of electron. If their electrons are same, their IDID are of the same strength, but their EDPD would not be of the same strength. Why? Because their electronegativity differences are different, right? And if the molecules are organic, then there is possibility of isomers. See, straight chain have more surface area of contact, branch have less surface area of contact, straight chain more contact points, branch has less contact points. Your next topic is how to compare the properties of simple molecule. That this I'm going to cover in the next lecture, right? And now don't forget to like, share, and subscribe the channel. See you in the next class. Allah Hafiz.